today's lesson, we are going to be looking at transformations of any function. So we've looked at transformations of quadratics, we've looked at transformations of sine waves. Now we're going to look at transformations of any function. So it doesn't matter if it's quadratic, sine wave, or anything else. We're going to look at how we can graph the transformed version of that. So in general, the general form of a transform function, so if we're given our base form of y equals f at x, it can be transformed by having y equals a times f at x minus c plus d. So the three variables that are affecting our function or transforming it are going to be a, c, and d. And again, you should feel like this formula or this function looks familiar because it's very identical to the quadratic formula that we were using for transformations, as well as the sine formula. Right? So it's essentially the same thing, and it's reflected in their transformations as well. We see we have the same values for the same transformations for the different values or variables. A still refers to a vertical stretch if it's greater than 1, or compression if it's between 0 and 1, and it also represents a reflection in the x-axis. Right? And remember, if it's negative, it's flipped. C represents a horizontal translation or a shift left if C is negative, or right if it's positive. Again, remember for the C value, this is something where, because it's in the brackets, it's the opposite of what we see. Same thing as it has been for the sine wave and for the quadratic function. D represents a vertical translation or a shift up when it's positive, or a shift it down when it's negative. Right? So again, same transformations. Now we're just applying it to any function. Now, if we had a table of values, or if we weren't quite sure what to do, going from a specific function from one to the other, we can always come up with a table of values for our base function and then apply the specific transformations to certain values for our transform function. So let's say, for example, we just had a base function of 0, 1, 1, 1, 2, 2, or 0, 0, 1, 1, 2, 2, and 3, 3. Very basic function. And we have our transforms function. Let's say we have an a value of negative 2, f at x minus, keep it simple, 3, plus 4. So those specific values affect different coordinates of our points, right? So the minus 3, that actually affects our function because we have, by shifting it left or right. So that affects the horizontal values, or the x values in this case. So we take our c value and add it to x. The a value, again, that represented a stretch or compression vertically. So we multiply our y values by whatever the a value happens to be. And then we also add our d value because that's going to shift it up or down. And then again, that's only affecting our y values. So different transformations only affect different parts of our coordinates or parts of our points. So if I look at this function that I just kind of created, our a value is negative 2, our c value is 3, and our d value is 4. So if I apply those different parts, so my initial x value, 0, and then I'm going to add c, so 0 plus 3 equals 3. So that's my new point or x value for this original point. And I can go through the rest of them. So I'm going to have 0 plus 3 is 3, 1 plus 3 is 4, 2 plus 3 is 5, 3 plus 3 is 6. So my new values for this table is going to be 3, 4, 5, and 6. And you'll notice that every value has been shifted or is in the positive direction 3. If I look at the y values, I'm going to take my original y values, multiply them by a, so negative 2 times 0, plus my d value, 4, and I get 4, because 0 times negative 2 is 0. Negative 2 times 1 plus 4, Again, negative 2 plus, plus 4, and I get 2. Negative 2 times 2 plus 4 is 0. And negative 2 times 3 plus 4 is negative 2. So my new y values will be 4, 2, and negative, or 4, 2, 0, and negative 2. So those new coordinates, if I graphed them, would give me a transform function of this base form. Now, that's probably not always the easiest way to go about finding a transformation. It's probably easier when you look at it visually. So that's primarily what we're going to focus on. So there are steps to drawing the transform function or drawing the transformations. Again, similar to all the other functions that we did, we want to find key points on our base function. So again, those are points that neatly cross a grid line, where we clearly know what the values of the coordinates are. Then we're going to apply the vertical stretch or compression first. So similar to the table, we're going to multiply the y value of those coordinates by the a value. We're then going to apply our horizontal and vertical translations to each point. So after we apply that stretch or compression, then we're going to apply the left or right or an up or down shift. So let's look at a couple of examples. So we want to sketch the graph of y equals f2 f at x plus 3 plus 4 if this graph here is our base function. So this graph here is our base function, y equals f at x. We want to then draw the transform function that's listed. First, it might help if we list our transformations. So because we have an a value of 2, we have a vertical stretch by a factor of 2. Our c value is negative 3, opposite of what we see. So shift left 3. And the d value is 4, so we shift up 4. So the first thing we're going to do, we figured out our transformations. The first thing our step said was to find key points. So I could find nice values all along here, here, and down here. But I really only need kind of the key points. I know it's straight lines connecting kind of these vertices. So as long as I know these 3 points, if I transform them or shift them to where they should be, I can then just connect the dots and I would have my transform function. So it does help to know the values. So 0, 0, this is 2, 6, and this would be negative 5. Oops, not negative 5. This would be negative, not negative, 7, negative 5. So the first thing I need to do is I need to apply a vertical stretch by a factor of 2. So that means I need to take all the values and multiply them by 2. So whether you keep it to the side or if you want to kind of draw it in step by step. So if I apply a vertical stretch to the first value, y times 2, or 0 times 2 is 0, so my point stays here. 6 times 2 is 12, so that means I have a new point up here. Negative 5 times 2 is negative 10, so I would have a point down here. So if I was to hypothetically connect those dots, I don't need to do rows to do it quick. If I was to hypothetically connect those dots, I could see that my function has been stretched. It's been vertically stretched. It looks like it's been grabbed from the top and the bottom and pulled. However, I'm not done yet with any of my transformations. I still need to then apply the horizontal and vertical translations or shifts. So I know that each point now is going to shift left 3 and up 4. So each point I'm going to shift left 3, so 1, 2, 3, and then up 4, 1, 2, 3, 4. So this original point here, after all the transformations, is going to go up to here. This next point, I'm going to shift it left 3. So 1, 2, 3, up 4, 1, 2, 3, 4. That's where that point is going to go. So after all the transformations, this point is now shifted up there. And this one on the bottom, I'm going to shift it over 3. So a little bit hard, but we know we're at 7, so we're going to shift it over 1, 2, 3 to 4 and up 4. Yep, and then up 4. So we're at -10. We're going up 1, 2, 3, 4. We should end up right at about -6. So this point shifts over here. So those are where all those points end up shifting to. I can then connect the lines. Between those 3 points, and I now have an idea. Oops, let me just move this out of the way. I now have an idea of where or what my transform function looks like. If you don't like doing like this, you prefer it more analytical, again, you could create the 2 tables of values. I'll do it up at the top here, x, y. So our original function had 0, 0, 2, 6, 7, -5. Our new function would be x plus -3 or x minus 3. And our y value would be 2 times y plus 4. So we can take our x values. 0 minus 3 is -3. 0 times 2 is 2, plus 4 is 4. Move on to the next point. 2 minus 3 is -1. 6 times 2 is 12, plus 4 is 16. The next point, 7 minus 3 is 4. -5 times 2 is -10, plus 4 is -6. And we see that we have those 3 points, -3, 14, or -3, 4, -1, 16, and 4, -6. So again, regardless of which way you prefer to do it, using the tables and plugging in the values into those specific spots, or by applying the transformations directly onto the graph, either way works out to giving you the same values. The next one, we're going to be doing the same thing. This one we're more familiar with, but let's kind of go through the same steps that we looked at. So I want to find the A value, the C value, and the D value. In this case, my A value is -1, which just means I've flipped. My C value is +2, so shift right 2. And my D value is +5, so that means I shift up 5. Now we'll look at it going in both directions, or we'll look at using the table and just go by looking at the graph. So I want to find key points. So there's one there, 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 here, and here. And it looks like here and here. So those are enough points that I can accurately, or at least roughly, sketch out my graph. First thing I want to do is apply the transformation. So I want to flip the points, right? The first step is to multiply all the y values by -1. So in this case, I kind of just draw it in. 0, 0, 1, 1, -1, 1, 2, 4, 3, 9, -2, 4, -3, 9. So if I multiply all those y values by -1, they all just become negative. So that means here stays 0. I have a point at 1, or -1. this y value becomes -1, 2, or the 4 becomes -4, 4 becomes -4, 9 becomes -9, and same thing on the other side. So this red graph right now, this is just what it looks like when we apply our a value. And it does look like our flipped function, which does make sense. But now what we have to do is we have to shift this graph left 2 and up 5. So I'm going to take all my points, I'm going to shift them right 2 and up 5. So start with a vertex, go over 2, up 5. 1, 1, over 2, up 5. Next one, over 2, up 5. Over 2, up 5. And here we see half of our graph. Now, because it's a quadratic, and we can clearly see that, we can mirror our points on the other side or still apply the same transformations. So here we see now in purple, this is our transform graph. So I can take out these red points. And I have my transformed function from this original one. Again, if you prefer to do it by using a table, that is also okay. We look at our original function. We can write down some of those key points. 0, 0, -1, 1, 1, 1, 2, and 4. Actually, let's just write down one side, and then we'll just mirror it on the other side. 2, 4, 3, 9. So our transformed table will look like x and then plus c, so plus 2, and then -1 times y plus 5. So for the first pair, 0 plus 2 is 2. 0 times -1 is 0, plus 5 is 5. 1 plus 2 is 3. 1 times -1 is -1, plus 5 is 4. Next point, 2 plus 2 is 4. 4 times -1 is -4, plus 5 is 1. Next point, 3 plus 2 is 5. And then 9 times -1 is -9, plus 5 is -4. So I should find that those values are the 1/2 of my parabola, which, if we go through and look at it, 2, 5, we see 3, 4, 4, 1, and 5, -4. And then we can mirror that on the other side. So I could do these changes in the table and then just go plot those points, and that would be my transformed function. Again, I could also draw it out and apply the vertical stretch or compression, then shift each point left or the horizontally and vertically. We'll look at one more example. So looking at a sine wave, again, we can list our transformations first. What do we see? Well, we don't have an a value, or a is 1, right, an invisible 1, so there's no a value change. We see a c value of +2, which means it shifts right, or not 2, 3, shifts right 3, and a d value of -2, so it shifts down 2. So if we're just going to focus on transforming it by drawing it, we want to find some key points. We don't really have too many because it doesn't neatly cross any grid lines, but because we're not applying any vertical or horizontal, any stretch or compression, it won't be too bad. So we are shifting it. So we don't. Because our a value is 1, we don't have to apply any vertical stretch or compression, so we don't have to multiply our values by anything. That just means we can take each point and shift it right 3 and down 2. So I'm going to take the first point, go over 3, so 1, 2, 3, and down 2. Take my next point over 3, so 1, 2, 3, down 2, 1, 2. Next point over 3, 1, 2, 3, and down 2. Next point over 3, so 1, 2, 3, and down 2. And final point over 3, 1, 2, 3, and down 2. Connect those points, and we have our new function. Again, if you prefer not to use the drawing method, you can always just create the two tables. So the first one will be our base function. So we had 0, 0. We'll kind of estimate we had 1.2 and 1. We then had 0 and not 0. We had 2.5, we could say, and 0. We'll just do one more because we do have a lot of points. We could say, so 1, 2.5, say 3.5, and -1. When we apply our transformations, the x value, we would add 3 to it because x plus c. The y value would be 1 times y, which is just y. So then, and then plus d, in this case, is -2, so y minus 2. So take the 0 value for the first point. 0 plus 3 is 3. Y minus 2, or 0 minus 2 is -2. Take the next point. 0 or 1.2 plus 3 is 3.2. 1 minus 2 is -1. 2.5 plus 3 is 5.5. 0 minus 2 is -2. 3.5 plus 3 is 6.5. -1 minus 2, or sorry, -1, minus 2 is -3. So if we look at our graph, we should have the same thing. However, it appears that we don't. We don't seem to have the same values. So something kind of went off here. And I think the issue is because we misread the scale, right? We got to be careful of the scale because every 2 blocks is considered 1. So we want to be careful of that. So we actually have to go back and change this. Luckily, we do have our nice point, so we can easily graph it. Remember, when we're shifting it, we want to make sure we shift it based on the scale, not just the squares. So a good learning moment. So our first point will be at 3 and -2. Our next point is going to be at should be 3.2. Sorry, it should be 4.2. Making mistakes all over the place here. So 4.2. So 3, so 4, 4.2, and -1. And then 5.5 and -2. And then 6.5 and -3. And we know we kind of have it building back up. So we'd have another one over here. So this is more what our graph should look like because we're shifting it based on the scale, not just the number of squares. So we want to be careful of that. In that case, sometimes the table might be more helpful because we don't have to worry too much about counting squares. We can just figure out what the new value should be or new coordinates and apply them to our points, or just plot our new points. So the main thing from this lesson is just how to transform any type of function. Given a table of values, or even given the graph of a function, we can always get a table of values. We can then apply the transformations directly to the coordinates, or we can apply the transformations to the coordinates on our graph by multiplying first by the a value and then shifting left or right and then up or down depending on what our c and d value are. So whichever way you prefer, whether you're using the table of values first and applying those coordinates, or by making those transformations directly on the graph, either way works, provided you do get the right answer. So there are some practice questions in the note. So again, please make sure you are going through and practicing it. It doesn't help just to watch the videos and copy down the notes. You do need to make sure you're doing the practice so that when you're given other types of functions that don't necessarily look like this, you can still apply the same process.